So this is section 4, lecture 22, decision tree, and I will cover a little bit about bagged decision trees. So this is the module 1 for this lecture 22. So we are in the last group, discriminative classifier group, and we already covered finished generative classifier and instance-based classifier. So this is the nutshell of decision tree, and let's get started.
In a nutshell about decision tree, what we cover, it's mostly for classification, and the fundamental idea is to partition the feature space into sets of rectangles, and then using this intuition, using this assumption of local smoothness to perform the prediction. And it uses, in terms of learning the model, it mostly relies on greedy approach, greedy search strategy. And it has various kinds of measure to figure out how to build a tree. And the fundamental component is what to use to split a feature into, using a feature to split data sets into children, into children node. And there's an idea called information gain, Gini, and chi-square, or cross entropy, which you already tried in the homework 4. And the final model, it normally is a tree. It looks like it's essentially a space partition model. All right, so this is the roadmap we're going to cover about decision trees. So first, we're going to talk about what do we mean a tree representation, and then we are going to have a pretty quick review about information theorem and also how to use information theorem grounded measure to learn decision trees from data. And then we're going to expand basic decision trees with the techniques called bagging, and then even further go to a much more practical ensemble of decision trees, which is a very powerful baseline model called a random forest. And then next time we're going to talk about even more powerful and more popular model called XGBoost. So this is the roadmap. So again, let's just compare these tree-based models with others. So this is an old benchmark paper in 2006, but to give you a good idea about how the different classifiers compare to each other on the smaller or medium scale data. So in that benchmark competition, all the top winners, all the top group of classification method on this small scale benchmark data are tree-based ideas. The first is bagging, decision tree, random forest, and then just variation of bagging and random forest combinations. And then this is a more recent conclusion, which from this pretty important guy called Frankos. You should check out his Twitter. So anyway, let me just summarize what he always used good figure to summarize top platforms or top compare different platforms. So like in 2019, so he's a big fan of Keras, which you already tried in your homework. So this is what from his recent figure summary, saying the primary machine learning software tools by the top 5 teams on the Kaggle competition. In each competition, like it's Keras, then is called a light GBM, then XGBoost. Both the second and third are tree-based package. It's a very, very powerful tree-based platform using distributed idea back grounded using multi-threaded structure. And then later there's PyTorch, TensorFlow, Scikit-learn, Phi, and some. The blue colors are not deep learning, and the orange colors are deep learning platforms. So, so this just trying to tell you, So tree-based idea maybe sounds kind of vintage, right? It means trees, almost the oldest classification models from machine learning, but in fact, they are the most popular and mostly used in industry besides deep learning platforms. And they are also very consistent winners in a lot of Kaggle competitions. All right, so before I talk about concrete decision trees, I want to tell you not just about the prediction performance. There's another reason why people like decision trees. It's called readability. So, so there's this. This is actually from scikit-learn. They kind of put different classifiers, simple classifier, in this coordinate called readability. So it put k-nearest neighbor as the lowest because k-nearest neighbor just gives you neighborhood structures. It's really difficult to understand why two classes and there are two classes. And then the quadratic type of classifier we covered in Gaussian generated base classifier called QDA, generate this kind of quadratic decision boundaries. So it's very easy to tell why their two classes are separated, because you know the center, you know the shape through the covariance matrix, but it's still kind of complicated, and because you don't know why it's more towards the upper, because actually in this case it's because the covariance matrix is more rounded in the upper class, and covariance matrix on the lower class is much more stretched. So, and then the other going higher of readability is the linear classifier. It's just super easy to understand. We're using a linear decision boundary to separate two classes. And then the decision tree is even easier. It's actually even more readable than linear classifier. And then we're going to talk about why it's even more readable, and especially for us, for a more computer science logic trained mindset. All right, so our famous tennis playing examples, and then last is our why. And then, so here I label you with all the yes training examples, and we're going to build a decision tree to represent those logics represented by the features, and also the decisions is about play tennis or not in the next slides. All right, so this is the model, summarize everything before, summarize the previous training samples. So in the naive Bayes classifier, we are using conditional probability to summarize the relationship of features to the output y variables, right? So there is py conditional on. So we are trying to model p play tennis, and given the outlook, given the temperature, given the humidity, and given the wind. So that's the naive Bayes classifier, how we model those. And then we use argmax MAP rules to perform decision. So, but in decision trees, it's just a tree. So here, each node is a test on a feature or on a variable, and the outlook feature is on the top, right? There are only three kind of choices: sunny, outcast, or rain. If you pick the outcast, and it's just give you a completely determined decision, which is yes. So let's come back to see this figure. Play tennis, and those are the yes entries, the yes samples. Let's check out outlook equals to, for all these 5 cases, 4 cases, if they're all this outcast, all the outlook variable is the overcast. So that's the reason why we got this branch. If the outlook is it's overcast, it's very determined. It determines we're going to reach a decision, which means yes. So we normally write, so in this decision node, we normally will write how many positive samples are here, how many negative samples here. What I meant positive versus negative is my Y decision. So in this case, I have if the outlook equals to overcast, there are totally 3 yes and 0 no, right? Because let's look at the outlook equals to overcast. There's no other cases overcast corresponded to no, right? So whenever outlook equals to overcast, the play tennis equals to yes. So this means when the outlook equals to overcast, I got yes decisions, and then that represented as 4 positive and 0 negative from my data. So this is how I normally see, I know the distribution of that yes decision is supported by 4 positive training samples and 0 negative training samples. Question about this, and this is very important. This 4 positive, 0 negative, and we're going to counting this type of positive versus negative for each one of the nodes in the tree. Okay, because this is fully 4 positive, 0 negative, that's why this is a yes node. And let's come back. You can do performing this again and again for each node and writing out the numbers of positive and negative for each of the node there. So for example, the top node outlook, essentially, if you still remember when we did this counting, this node represents all the training samples, right? So how many positive here, how many negative here? If you still remember the table I shared. 4 positive, oh actually no. 1, actually 9 positive, 5 negative. Yeah, 1, 2, 3, 4, 5. Yeah, it's 5 no, sorry. So this is 5 negative, 9 positive. So you write this like this, that's my top node. And then after each split, this goes to 4, 0, and this goes to, yeah, I need to do all the contents, but let's see the next page I did. So 14, which is 9, 5, and then this has 5, and this got split into further. This goes to 0, positive, 3, minus, and this goes to 2, positive, 0, minus, and this is 4, 0, and yeah, you can do the same counting. You can perform this positive, negative on each node on this tree. And the whole reason why we get this tree is actually depends on this positive versus negative numbers. Alright, so this is a summary of the tree and how my training data actually can be represented by the tree. Yeah, question about this. And all those nodes are pure, which means either positive 0 or negative 0, those are the decision nodes. Those are the leaf nodes. Okay, so this is really intuitive, right? I mean, completely intuitive and readable. So from this angle, we can see, and this type of model is easier to read and easier to understand why some got predicted as positive, some got predicted as negative. And then how do you use the model? So when you have a new test sample, it's really easy. You just go down the tree according to the feature values of that test sample. So in this case, it's a sample with outlook equals to rain and windy equals to false. And then your outlook is the rain, go to the right, rain go to the and then you got the windy node, and wind equal to false, you go to the right, and this gives you a decision yes. It's really simple, and also it gives you actually the path that you take, the decision steps that you take to arrive at the decision. All right, no question about this? Okay. If you have another sample as outlook equals to overcast, it gives you just one step and give you the yes. And then outlook equal to rain, it can give the yes. So in fact, on this tree, there are only three, it's actually represented three different cases to arrive yes, which is these three cases. Outlook equals to outlook is class of outlook rain and wind is a false, or outlook is sunny or humidity normal. Okay, so what does this even mean? This means it's essentially the decision tree on this kind of discrete type of data is representing as a disjunction to represent a set of rules, and each rule is a conjunction on the attributes of the values of interest. And you can totally rewrite the decision tree into this. This is the yes case, it's a Boolean function, right? This is the first and the or, second case and the or the third case. And this totally reflected by the tree. Okay, so that's discrete case. On the continuous case, what the decision tree really are. So on the decision tree, on the continuous case, so let's use a classic decision tree called cart. And the cart essentially just, for the first, it's still a tree. So just give you an example tree. On the top level, it uses a threshold point separate the space into two. So that's essentially here, x1, t1 separate into smaller than t1 or larger than t1. So that's my first top level node, what it did. And then on the left, using x2, so on the left is using the second feature, and it's equivalent to, and separate this rectangle into two rectangles, upper R2 and lower R1 region. So this is essentially the left branch of the x1 of the root node. When x1 smaller than the t1, it's separated into further by the x2. And then on the right branch, you can continue to separate using x1, using t3, another threshold. And then you just separate further using the actual x2, using a t4. So in the end, it's equivalent to segment the whole two-dimensional space. In this case, there are only two variables, right? It separates two-dimensional space into sets of rectangles. And you can represent, so each rectangle share the same prediction. And then that's exactly the surface map this is trying to represent. So this is the R2. Yeah, I think that's R2. And this is the R4. And they share the same prediction values. This is more a regression formulation. And then the middle is the R3, and then R1 and R2. So what the fundamental idea is kind of summarized is the decision tree partition the feature space into a set of rectangles. In the discrete case, it's separated into disjunctions of rules, and each rule essentially is a conjunction of the Boolean conjunction of the values of the variables. And this kind of process essentially is a tree. It's a tree representation of the rules. Question about this? All right, so this is really easy to explain. So that's why in the beginning of the machine learning, or when there's a more applied task, people care about how to do the interpretation. Normally, those applied scientists prefer to start from tree models. All right.
Great. So this is the end of this module. See you in next module.